Hello everyone, welcome to another Kent Seminar Series. Today, our speaker does not need an introduction, but I will remind everybody that Professor Ouyang has been teaching here. He has been faculty for 18 years and is now the George Krambles Professor of the Department of Civil Engineering. He earned his PhD from the University of California in Berkeley, 2005, and his work mainly focuses on planning, operation, and control of complex transportation and logistics systems, with applications to agricultural, energy, and urban infrastructure systems. So please help me welcome Professor Ouyang.
Thank you very much for the very kind introduction, and it's always great to be here and then to share some of the work we have been doing. And then I realized that this work has been part of a project that we are collaborating with many of you. So I hope I'm not going to bore you by repeating it, but hopefully there were some interesting questions there that we're addressing. So this topic is about the last mile delivery by drones. And then I hope this is something in the media a lot that you have been aware of it. But anyway, we're going to give a quick introduction about the background and then quickly go over to some of the research questions that we're trying to address, and hopefully you see that this is actually probably something that's of interest. So I want to acknowledge that this is joint work with, again, I mentioned Dr. Cardi was leading a project we are funded together through Michigan, and also several other things. National Science Foundation has also been supporting my earlier work in this. So just want to acknowledge that, and also my PhD student Yanfeng Ouyang has actually been the force behind all this work. He did all the work, and then I want to acknowledge his efforts here. Just a little bit about the background. So freight delivery it typically involves a sort of multi-echelon of shipments. So essentially that we have supply and demand points, and then we try to find out the best way to ship the goods from the supply points to the demand points. And very often our question is how do we actually go through these multiple stages of it? And then it has been well known in the logistics literature that actually the optimum, near optimum delivery systems, if we look rather from this schematic view, rather into the spatial view, then actually logistic systems will benefit from this sort of hierarchical structure. The hierarchical structure would actually try to divide the delivery into two parts at least. The one part is the so-called line haul part. The line haul part actually is a long distance travel. We use large volume vehicles with high capacity, very cost efficient, and then try to cover long distances, carry a huge volume over it. But then this type of vehicles normally would not be suitable for door-to-door delivery. You don't want a truck to visit you every day, do you? I hope not, because it has a lot of implications about safety and energy efficiency and so forth. So then the last mile, which is actually the part where you use a large vehicle to deliver to a neighborhood of customers, and then you use smaller vehicles. You desolidate and then you break the bulk, and then use the last mile to deliver to the local customers. And this local sort of last mile, it's actually much shorter in distance overall. If you look at a delivery system, the line haul distance covers most of the distance, item distance travel, ton miles, whatever you call it. But then the last mile is very short relatively in distance, but it actually is more costly because you have to use smaller vehicles to visit the customers, and it's less efficient in terms of cost. And actually, then it actually turned out that last mile delivery covers more than half of the total cost, just because it's less efficient. So it's an important part of the puzzle. And then particularly in recent years, especially after COVID, with all the information technology booming, and with COVID, actually last 3 years has been really changing the landscape. E-commerce has been booming in our world across the board, everywhere. I'm sure you order much more online than you did before, a few years back, I think. At least I see that happening to myself. So actually this has been a trend, and we think this trend probably will continue even after COVID is going to end soon. And then in the US alone, just to give you a little bit number, that essentially in New York City, one city alone, every day, there is 1.5 million parcels or packages being delivered on a single day. So you can just imagine how this has been changing. In the past, you go to a store and buy it, drive there, pick it from the aisle, and then go out. But now it's actually delivered to your door, more and more so. And then then the last mile delivery, mostly in the past, has been be dependent on the vans. In the United States and in some other countries, use other type of small vehicles. Again, they use smaller vehicles because we need the flexibility, and we need to be responsive to the demand. And then for the last mile, and you have to fit into smaller roads and so on and so forth, and then for safety reasons and so on. So typically we have been using this type of smaller vehicles to do the last mile delivery, but then there's issues associated with that too. So for example, there's less efficiency, and then you need a driver in it particularly. So hopefully the autonomous vehicles is going to change the landscape a little bit. But anyway, there's also that this type of small vehicles often exacerbates congestion in the local neighborhood. That's actually an issue. Has been reported in many countries that the local traffic actually are caused by a lot of deliveries in many cities. And also safety hazards as well. There has been, I know that in China, there has been media attention about, those local delivery people get killed or killed somebody in that regard for the last mile delivery. So there are all kinds of issues associated with that. And then, of course, then like any other industries, we are sort of really seeing the revolution as we go along. Sort of one of the opportunities that are actually sort of presented to us is autonomy. And then this is actually the project we have been working together with many of our colleagues here regarding sort of using autonomous vehicles and UAVs as the sort of the next generation delivery vehicles. And then those of you who are familiar, we have been actually working together with through the project about how we can make truck platoons for the line haul part, and how we can use local UAVs for the last mile deliveries. And then for today, we want to stay focused. We will not talk too much about the platooning part. We have a number of us excellent work has been done here regarding the platooning, but then here we are going to focus on the last mile, the delivery by drones. So with that, I just want to mention that actually drone delivery is happening. I don't know how much you follow the media, but I actually updated this photo. I used to have a video here just to show you it's actually happening. But I actually updated this. I don't need the video. You can find it online anywhere. It's everywhere in the internet. But I just want to remind you. I like this reminder. This article was actually 6 years old. So 6 years ago, exactly 2016 December, the first commercial delivery by Amazon was actually conducted in UK, and then a 5-pound package was delivered 7 kilometers within about 30 minutes. The 30 minutes is from the time that's ordered. The order was placed and then to the delivery to the door. So essentially, it's very fast, 7 kilometers. This sort of shows the promise that we can do very responsive delivery based on e-commerce. Then later, the UPS and has obtained the commercial sort of a license and or the permission, I should say, approval by FAA to the delivery in 2019. 3 years later, two plus years later, and then they have already been doing pharmacy delivery starting from 2020. So this is just this is happening. I don't know if you follow the news, and also I just noticed actually also in other parts of the world and in China actually I noticed that Shenzhen, one of the cities in China in the southern part, last year in about 9 months they have delivered 80,000 food delivery parcels, like a food delivery in about 9 months. So this is actually happening very rapidly over the past few years. There's a huge penetration into the market. So we think this may be one of the promising futures. And then so let's look a little bit about the pros and cons of UAV-based deliveries. So advantages, obviously, if you really look into the numbers that actually all these companies are publishing, it's actually surprisingly cheap and fast. The drones can travel at least 100 miles per hour, roughly. That's actually faster than the fastest cars you can allow to drive on the roadway surface. Thank you. And then it's actually also cheap because actually really it's electricity driven mostly, and then it's really the cost is low. And then particularly it's flying in the air. Hopefully that really alleviates a lot of the congestion issues we have nowadays in the neighborhoods, and also safety issues and also sort of the COVID-19 less human intervention in the middle because it's all automated, obviously. So these are all the great things about it. But then obviously you can see actually from here that the cost really it's Amazon estimate is about $1 per delivery. The cost for the delivery is actually cheaper than any of the other options they are using right now or in the past. And you can see some numbers here. But drones are not really the silver bullet either. And we are, as academics, we're always skeptical about everything, right? So drones also has its shortcomings, obviously. The first one is that it has a weight limit. Of course, it cannot carry like a car, obviously, right? Go to a door. So there's some weight limits. This is something that needs to be dealt with. But also there's also limited flying height and range. So the drones cannot fly too far because still it's flying. There's a limited capacity in the batteries. And also, so this is some of the issues, but one of the issues that actually the industry probably didn't realize too much is that actually, although we are now shifting the delivery vehicles from the surface roads to the air, it looks like great, but also we should be aware, this is actually the work that we are sort of motivated to do here, is actually we're just shifting traffic from the surface roads to the air. And in the future, if this really going to happen in a large scale and commercial scale, then there will be congestion potentially happening in the air, just like how the airlines are currently congested. So you can see all the drones flying around. How do we even manage the traffic in the airspace? It's going to be a problem, I think. And FAA, I think, recently has been sort of looking into this problem. How do we allocate airspace to allow drone traffic for different purposes? So that sort of motivated a few years ago. We motivated us to look into this problem. And then some of the solutions that the industry has proposed, not us, but industry proposed a few years ago, particularly to address the issue regarding limited range and height, is to, again, use the idea of a big vehicle covering longer distance, heavy loads, and then using drones only to do the last mile, really the last mile or last 500 meters. The idea is actually we can combine the traditional trucks, let the trucks go further into the neighborhood, and drone only fly a short distance. This is partially the solution UPS has been doing in the past few years, sort of designing new type of trucks that can dispatch drones and so on. And then Amazon went a little bit step further. This is a patent that Amazon proposed. It has been a few years. They've patented like maybe 5-6 years ago, so-called the floating warehouse. I always, when I see this picture, I think of the movie Independence Day. Sort of the bad drone that are attacking us. But think about this mothership that's flying around, and then the drones just fly out of it and then serve us. Okay, so this is the sort of what Amazon had patented a few years ago. The idea is actually we can use this bigger vehicle, even bigger than the truck. I hope you see that actually there's a certain economies of scale in terms of carrying loads. And then this air, whatever the floating warehouse can go around the city, float around, and then drones can take off and land from the ground and then to the mothership. The benefit of this type of system compared to trucks is actually when the drones are going back, it's without any loads, hopefully, so that it's more economical to fly up. And then the loads are already carried by this floating warehouse uplifted into the air. Then when the drones is actually carrying the payload, it's gliding down, so the energy can be saved a little. So that's sort of the whole idea, using economically sort of more efficient modes to lift it up, and then using drones to glide it down, right? So that's sort of the idea. So there's some sort of benefits and merits in it. So anyway, so these things are actually happening. But then the question is, now we have all these ideas, how do we actually make them work, really? Now we just imagine that we have here we're gonna call trucks, but really the truck doesn't mean really truck. It could be the floating warehouse, whatever big capacity mothership that can fly around, and then drones coming out of it. Then there has been actually in the past just 2-3 years, there has been several a lot of people looking into this, how we can make trucks and drones work together. That's actually a big research question, right? So if you imagine that actually, these are just some examples to show, you could have some depots still, like warehouses, local warehouses, and then the trucks can go around and deliver, and drones can fly out to deliver. And what are the best way to combine them? This is the question. So people have been proposing different ways. A drone directly ship, but there's a limit to the distance. Trucks can go out and then deliver, and then somehow combine them together, and then somehow whatever ways you can put them together. So one of the promising way I personally think is actually that we can have again the truck. I use truck again to represent any big ship that going around, and then the drone can fly out, and then essentially the truck is moving, the drone is moving, and then they just go deliver jointly to all the customers in a certain neighborhood, and then essentially the drones only fly a small distance as needed, but then the truck covers the most of the distances needed. So this is sort of one possibility. Another possibility is actually we have the truck going around, but then the truck could stop somewhere, turn themselves into a temporary launching pad, and then the drones go out and then deliver. So it's like the truck go and stop, and then drones go out and come back and then move on and to another place and do this. So this is another possibility. So these are all sort of people's ideas about how drones and then trucks or floating warehouses should work together. So we are actually interested in this, and we looked into it a little bit and see, all these different ways of sort of making trucks and the drones work together. What is really the efficient way to do it? That's one of the questions we have. And if we were to do it in any of these ways, how should we do it actually? And what is the engineering solution we should use to really do it? So first of all, I want to mention that actually, we could have truck only, UAV only. This is really like one of the ways to do it. This is really the generalization of these two. I hope you can see that you put this. Either of these two is a degenerated case of that, right? And you can see that. And then this is actually the horsefly problem where the truck goes around. But then this one, the truck actually stops from time to time, and then the drones go out. But this one is almost like the truck keep going, and drones go out and then try to catch the vehicle, the truck as we go along. So these are sort of different systems that we can use. So it turned out that actually, what are we going to do is that we want to look a little bit into this system first, maybe as our first question to answer, is that if we were to do this type of system design, so the trucks go out and then temporarily stay somewhere and then let the drone go out, what is the optimal way to do it? And then so this leads to this research question actually, is that actually suppose we have this question is sort of the basis for the design, is that suppose we have a homogeneous area of space, just for the property of mathematical system, is that essentially if you have a vehicle, the truck or the floating warehouse that's going to be going around, how should this floating warehouse go around? What is the best way to route it around? We want to save some distance that this truck itself has to go. Let me use truck route. That means the big vehicle. The truck is going to go around, and where should the truck stop? And how frequently they should stop? And then each time the truck stops, then the drones go out to serve the customers. And then how big this area should be and what shape it should be. This is a computational geometry. Then how do you partition space into small areas such that you have this truck routed through it and minimize the total cost for truck routing as well as the drone travel. I hope this makes sense, this problem. So this problem, we started looking at this around 2015. And then we use some, I'm not going to bore you with the details, but I actually have a little quiz for you, but I forgot. I was going to quiz you all. Like say, if everything is homogeneous, what do you think this shape should look like? Roughly would be near optimal. I already reviewed it. I apologize. I meant to. So there has been some research in computational geometry showing that if distance is measured, if drone really should be using the Euclidean distance, that means going in straight lines, right? Then actually hexagons is supposed to be good if we do not worry about the truck routing. But if the truck routing is actually under consideration, it turned out that actually this is not optimal. I'm going to show you. So we have some results from the literature about how the space should be partitioned, but it didn't really consider the truck. So what we did in the past few years is about how we can route the truck. And then, so there's some work that we did, and then essentially this, I'm not going to go into the details, but just tell you, interestingly, it depends on if the drones are flying directly, if we do not worry about the truck at all, truck is free, then we should have hexagons. If the distance is by straight lines, if the the drones have to fly according to a lattice, that rarely happens. But if that's the case, then we should have this type of diamonds or slanted squares. If we also consider the trucks are going around, you understand that actually we have to find a way to connect all these dots. That's a truck movement. If we worry about this distance, which is a cost, then actually hexagons that are squeezed would be optimal. We prove that it's near optimal under different situations. And basically, we prove that it's optimal. So this gives you some guidance, under different situations, under different costs, then you should actually partition space in these different ways. So that's sort of some of the work we did, just to show you that actually we did prove it in a way through some simulations. Then we have some random points. Then we try to 2,500 points in each of this square. Each point is a customer, and then we try to perturb all these solutions randomly, such that we look for the lowest cost. And then it turned out that actually this is the optimum partition. This is like a truck going around. This is the best solution we can find. I hope this makes sense. If you look at the areas inside this in the middle, the boundary has some effects, so it looks weird. But in the middle part where boundary effect is small, then it turned out that actually the shape and the angle and everything is very much close to our theoretical results. We proved that the optimal shape and angle and everything. So we have a formulas to describe how we should partition space if we have different costs. So you can imagine the more costly it is to route the truck, the more elongated and narrow this should be. So there's some relationship formulas we have. So it worked for different metric space and so on. You can just intuitively see that it's matching our theoretical predictions very well. So we saw that we solved a little bit of that problem. Okay, any questions so far at this point? Yes.
If I may, what are the parameters that you control when you perform the simulation? Is it the time that is required for the drone to go and come back?
It's a distance so far. We use distance everything. So everything there's a cost associated with the distance of drone flying out and also the track moving distance. So you imagine this solution I have, I measure the total distance of the track movement. I measure every point here to every point in here, then the distance of the drones, and there's a cost coefficient of each distance, and then we put them together. We minimize the summation of the two. Those coefficients dictates the shape of it, and we have some formulas for that. So, yes.
Was demand taken into account? Because the shape will vary or change if the demand was higher in one location versus the other.
Yeah, the demand actually for now is we assume that actually the truck is large enough. There's no issues. But just imagine it's related to the coefficients we're talking about, because we're measuring this line length multiplied by a coefficient, and then we have this drone going to every point. Then essentially we do the integral of this entire area over the total demand. So the demand is part of the weight for this part of the travel. I hope that makes sense in a sense. Okay. Yes. Oh, sorry. Yes.
Yeah, but when you are getting the drones off the truck, are you expecting them to come to the same location, or you are moving the truck at the same time?
Excellent. We are not moving the truck at this point. This is one system where the
Yeah.
truck goes there, become a temporary stationary.
Temporary stationary, this one, yes. Okay.
Yes. Any question?
So I was wondering if the truck's route is free in this simulations.
Hmm?
Is the truck's route determined by the simulation too?
Yes, yes. Overall, we are simultaneously determining the routing as well as the partitioning simultaneous. It's like you are having a clean slate, nothing, no decision whatsoever. You try to manipulate it however you can, try to find the best solution. We have a way to do that. Yes.
Okay, so just a quick follow-up, then what's the difference between these two?
Oh, sorry, I wasn't too quick on that. This is actually under Euclidean. So distance measured from this point to this point is actually by straight line. This is actually like Manhattan metric. You have to travel along the grid. So the L metric we call it. It's just distance is measured differently. Somehow more like if this actually applies more for the city streets where you have robots that actually going around, you have to follow the street like a grid. Does it? I don't know if that makes sense. Okay, last question.
Does this verification consider the weight limits of drone?
This one we didn't. This is just a pure math problem where we consider what is the best partitioning technique. So if there's additional constraints, we could add it, but we didn't in this case. Okay, very good. Thank you. So let's move on. If this is this is just some earlier work we did to show how to really partition space. But then just want to sort of, we are very excited actually. We have a formula. And then we have this measurement, actually we measured it, it matches very well with it. So that shows that actually we are able to cross-validate both sides. So the formula should be correct and the simulation is actually reasonable. But then we haven't addressed one of the issues. So this shows you up to the previous slide, we were talking about how you can make the truck and the drones work together. How do you partition space? How do you make it work? But we have not yet considered the issue of congestion that the drone may encounter in the future. Not now. Now there's no congestion. You see 2 drones, 3 drones in the air, no problem at all. But in the future, there may be a problem when you have really commercial operations on a large scale. Then we need to consider that actually just like vehicles, the drones, when they crowd, just like people, when we get into a very crowded room, it's very hard for you to maneuver around and then move around, right? So it's the same idea in airspace. When we suppose we have a depot, this is where the truck stops, and then we have to send out a whole bunch of drones to do the delivery. And then maybe around here in the airspace are too many drones, the drones have to slow down. They cannot travel at 100 miles per hour anymore. We have to slow them down, avoid collision, just like how you drive. So, but this problem is also new in some senses. Congestion is old. We know this for decades, how to model congestion. But we do not know very well how to address congestion in the airspace, especially with drones, because drones are actually operating in 3D space. They can travel in whatever trajectories. There's no given guideway or channel that drones have to follow yet at this point. If you drive your vehicle, you have to follow the lane, otherwise the police is going to give you trouble. But in the airspace, we don't have those things yet. The drones can fly up and down, left and right, however they like. So any direction. And actually the congestion can be caused by drones in all directions as well. In our transportation system on the surface, we have traffic that's conflicting each other, but we use signals to try to divide them anyway. So every vehicle at almost every moment in time is traveling in a channel. It's traveling in a certain corridor. The signal basically divides the different directions, but every moment in time, you're moving in one channel, right? In a way. But then this may or may not happen. There's no signals in the airspace. We can, this is up to us what we're going to do in the future. But in general, we don't have those things. And then drones may or may not communicate with one another. Drones may or may not try to find the best path for itself or for the whole system. So depending on how drones may actually find its own way, but just understand every drone has its own freedom to move around somehow under your control or to go around in the 3D space and then under congestion. Maybe drones are smart enough. We should actually guide drones rather than go straight to the destination. Try to avoid the congestion if there's a lot of drones in front of you. Try to go around, right? So this makes sense. But then this type of problem is sort of relatively new because we know congestion in a discrete network in a city streets. But then those type of models we have in transportation systems where we model for congestion in I-57 and so on and so forth may not be suitable for drone model because first of all we have traffic coming in all directions. The drones can go however they like, and also there's very little description about the capacity of airspace in a sense, like how many drones is too many for the drones to pass each other in what directions. It's just a slightly different setup of the problem. So what we did is actually we sort of utilize some of the ideas in the literature, and then we modified it to address this drone problem. We develop a so-called continuous model. Continuous traffic model to describe it. So the idea is, this is only a few slides that have a little bit math, but I will hopefully go through it really quickly. You don't have to worry. It's just actually imagine this is one of the location where drones take off, like launching location. And I suppose this is actually the area where this drone launching location, then the drones fly out to serve this area in this neighborhood. Then we can actually describe the local flux of let me just go a little bit quickly here. We can imagine that in every little neighborhood in space, there is we can describe the local drone traffic by a certain flux variable, just like a flux. And then we can assume that actually the travel cost of every drone in this neighborhood experiencing flux fx near x, then this is the transportation cost per unit distance. It's like travel time per unit distance, like a pace. Then this is essentially an increasing function of the flux. So essentially you have too many drones in my neighborhood, then I'm going to slow down, sort of that type of idea. So we have this sort of capturing that sort of local congestion. And in this regard, you can imagine that actually if this is the truck stopping location, launching pads, and then these are the customers continuously distributed in the neighborhoods. We have drones flying out, and in every location in the neighborhood, there's a flux, there's some flow going around. Then the speed for a drone to traverse that little neighborhood would be dependent on how many drones are in that neighborhood. So in this way, we will be able to address the issues we had regarding drones flying in all directions and then forming traffic and then causing congestion. And then we assume that every drone chooses the best path. The path can be any connected trajectory from the origin to the destination. We have no limit on how they should be traveling, no guideways, no whatsoever. But then we look for we assume every drone follows a certain rule to look for the best route possible. Every drone looks for the best route possible. They collectively form congestion in the air, but then every person looks for the best way to get out of it. So that's sort of the idea we have. Then we also can figure out sort of so-called potential function, essentially from every location to a launching, for every location of a demand, how far is the cost? How much is the cost in a minimum way to serve that customer? So we can set this up sort of like a continuous traffic flow problem. I'll skip this. And just to say, this is a model that we use, and then we are able to use this model to describe all this notation to describe the problem we were talking earlier. Every drone looks for the best way to reach its destination, finding a trajectory in the space. Then it can be described by a partial differential equation like this. It's actually pretty standard regarding it's based on conservation law and so on. Then essentially, but we can show, actually it's shown by some other people earlier, it's actually the continuous version of the so-called user equilibrium formulations. This is actually, those of you who have taken Professor Kanto's class, you probably learned about the user equilibrium, that how you find the best route in a network to reach your destination. when congestion is forming on the links. There's a discrete network version. This is a continuous space version where people choose the best path to go to their destination, subject to congestion. But just you have to trust me on this. Essentially, we are able to show this partial differential equation describes the optimal route choice of every person in a continuous space. And then with this, then we can actually do whatever we want. Actually, I'm very proud to show you, but don't worry about any of this notation. But this is an earlier slide. We were able to show under certain conditions, we can solve that partial differential equation analytically in closed form. But then it's not generally true, but for some certain situations when the congestion function follows certain forms, we're able, I'll skip all this, we're able to solve the problem analytically. I want to show this picture just so you get a sense how, if suppose this is the area where demand is everywhere, this is where the truck is stopped, then the drones fly out or fly in, whatever, both ways. Then you can see this is actually the optimum way the trucks should be following, the path they should be following. This is actually a closed form analytical solution. This is actually the cost surface. In a sense, this is where the truck is parked. As you move away, customer from here will travel the least cost way to the truck, the drone. I'm sorry, I should say the drone go the least cost way to go to the truck. This is the cost value surface. And as you go farther away, there's more cost, obviously, right? But sort of the idea, this is how the flux goes. Just to show you some solutions, this is also an analytical solution when we have arbitrary shapes of the area, like this is a made up shape, but then you have two trucks that are sharing the airspace, serving the demand. You can see somehow some of the drones should be flying in a curvy way, just to avoid, there's a lot of drones in front of me, I should go around it a little bit, but you don't want to go too much around it. You go a little bit around it. What is the optimal path I should follow to get to the truck? So this is sort of some of the analytical solutions. For our problem, we actually didn't really rely on the analytical solution because it requires certain cost structure. We actually, for our project, what we did is that we actually studied a more arbitrary cost function like this, just this is almost like a PPR type of cost. Then this is like a truck stop location, and we consider a dome around it. And then so that we can imagine the customers are scattered in this area. That's my delivery customer. Then the truck is going to dispatch drones out, and then we can solve. We basically then I'll go really quick. We can build the how do we solve partial differential equations by an element method. So you guys are all experts. I'm not gonna bore you with it, but I think you can see we build this type of mesh, and then we use that type of elements. And then we were able to solve the problem, and then we were able to find out actually, for example, we can trace how if a customer is here, how the drone trajectory should look like. See that the issue is that the drones are no longer flying near the surface of the ground. This will be the least distance way of travel, but because there are going to be a lot of concentration of drones around here, so they have to go up and down to avoid the congestion near the surface of the roads. Anyway, so just so you know, we even I don't know if there's any questions up to this point. I have been moving rather fast. Okay, if not, then we continue. Then we actually did a lot of just for the fun of investigating the impacts of different factors. In the urban settings, we may have actually barriers in the urban setting. We may have buildings around, and even if there's no building in the rural area, maybe FAA would have some requirements regarding certain airspace cannot be used, right? Like virtual barriers. So actually, we were interested in knowing like what type of barriers actually, what would be the impact of the barriers. It's also actually interesting, those of you who have been familiar with network models, when congestion is present, having some restrictions on having some presence of barriers actually turned out to be better for the traffic. This is called the Bayes paradox. In a transportation network, you sometimes shut down a bridge. Everybody is actually better off overall. So that's actually because people are self-interested and they behave for their own interest rather than the system-wide interest, right? So those of you who are familiar with relate to that. We were also thinking that maybe with the barriers, or FAA should actually think about adding some barriers to something in a certain optimal way, such that actually the traffic can be improved overall. So that's actually what we did. And then we were trying different, like openings, we call this openings, like in a certain circle, what percentage of the area is actually having barrier, what percentage is not having barrier, this versus that, and how high this barrier is going to be, virtual barrier. Then it turned out that we tried all these different combinations. This is sort of traffic, like different ways of seeing the different barriers. We tried different numbers. It turned out, and we also can evaluate the energy consumption as a drone is moving up and down with or without a payload, and then maybe all kinds of movements. We can measure the essentially the energy consumption along the way. It actually turned out that actually I just want to show you a little bit. It's interesting with some barrier. Sometimes when it's actually optimum in some cases. I'm not going to go into the details, but in some cases, having a certain amount of barrier is actually the best. There's the optimal amount of barrier you want to add. If you add too much barrier, you're blocking everybody. This is not going to work. But then if you don't add any barrier at all, it's not good either. You want to have a small amount of barrier sometimes to streamline the traffic. It turned out that things work the best. So this is some interesting results we found. You just have to relate to Bayes paradox. That actually does. This is actually sort of show of a Bayes paradox there. We also I'm going to go very quick now. So we also showed that the Amazon floating warehouse. Remember, that's another motivation we study this. Then essentially this type of floating warehouse, we were thinking that really the model, all the changes just the trunk goes to the air and then gets dispatched in the airspace rather than on the ground. And then we basically build the same type of a mesh and then similar meshes. And then we have traffic description and so on and so forth. You see how the drones sometimes to avoid congestion here. We go around and then land from above the drone. So you can see that actually congestion does have some effect about the traffic. And then we were able to actually play with this and then try, for example, how high the drone, the floating warehouse should be. If it's too low, the congestion around it is too high. But if you go too high, it's too far. There's no need to do that. So there's an optimal height of the floating warehouse that's actually the best for the overall system. So we can this very simple applications that we play with just for the sake of having a little bit insights about the system. And also lastly, I want to say before I move on is that this is I hope I have time. How much time do I have now? Oh, I'm sorry, I'll finish in 5 minutes. I apologize. Okay, so essentially let me say that actually we also, based on all the analysis, we were able to also show that how we should partition space. It turned out that this we believe are the optimal way. When congestion is present, we call the Kirby hexagons is actually optimal. So anyway, just to show you that some of the work we have been doing a few years ago. 5 minutes. What I'm going to do is really quickly go over the last problem I haven't touched. I touched the problem where the trucks go around and stop from time to time, and the drones go out, right? Like almost like flowers, like blossom, right? like that. But then it's also possible where the trucks never stop, but the drone has to catch up after the delivery. And so this is another possibility, and then we have been working on this in recent years. This problem actually is quite interesting. Is that actually you can imagine the problem becomes now the trucks keep going, somehow navigates through the air, the entire surface of this city, and then the drone go out and catch up later sometime. Right? So this is a very simple animation actually Yanfeng developed to show you how multiple drones can be dispatched from the same truck and to deliver to customers like that. So essentially, there is a big decision that we have to make. Obviously, is that actually how wide this should be? How wide this should be? Because actually, are you going to be, essentially you can route this back and forth many times, and then make this very narrow. Or otherwise, you can make this only a few back and forths, and then make it very wide. Then the congestion here could be very significant because you have too many customers to serve. Does that make sense to you? Okay. So essentially, that's actually some of the issues we have to address in designing this type of systems. And actually, one of the big questions is that how should the drones be aligned in the air? Like, what should be the optimal trajectory of the drones if they were dispatched from a moving truck and catching up that moving truck later? So these are actually some of the earlier slides. This slide probably was 5 years ago, but some people maybe 4 or 5 years ago. I was conjecturing that if there were no congestion whatsoever, drones should just go straight line like that. But then if there's congestion, maybe you can imagine there's more drones here than here. Can you understand what I'm saying? Because drones are going to this neighborhood, deliver customer in the neighborhood. Drones are also going there to deliver to the customer there. So here we have a higher drone density here than there. So maybe that density is going to have an impact because the drones traveling here will be slower than drones traveling there, right? So sort of this is the type of intuition we were guessing that this is the optimal trajectory, and we obviously was wrong. Okay, so we learned later, only like 3 or 4 years later, that our conjecture, this was the earlier conjecture, was wrong. It turned out that actually this reveals it. This is actually the optimal trajectory of the drones. If we have a truck that's moving, then the drones should be actually moving like almost like that shape, like that. I was thinking the other way around. Shame on me, but anyway, we made the best guess we could at that moment. But also there's also a lot of interesting questions that actually when you are designing this type of systems, you may want to make it work. You have a lot of issues. You need to, I already mentioned how wide the service range is going to be. I have a truck that's going, right? Then the drone's going out to serve customers nearby. How near is nearby? How far is to, how wide this should be? That's going to dictate how much truck is going to be moving back and forth to cover the whole ground, right? That's one. Also the trucks, what speed should the trucks be traveling at? And also another thing is actually how, another issue you probably don't worry about, but if you think about it, you could also have the different customers along this lateral direction. How you're going to sweep through the area, in a sense. Think about it. This is my service area. I'm the truck going around, and I'm sending out drones to visit you. And at any moment in time, a subset of you is getting drone visit at the same time. Think about it. I'm sweeping through you. We're using my drones. I'm sweeping through you. I could sweep like this. I could sweep like this. I could sweep like this. Does that make sense to you? And every moment in time, a subset of you is being visited by drone together simultaneously. Then how does that subset look like? That's also a decision that has some implications actually regarding, especially the drone has to catch up to the truck. So these are all decisions when we design the system we need to worry about. So without further details, but just to say we actually did some work. We first of all try to translate this system. This is actually from the perspective of a roadside observer. You stand on the roadside, you see truck moving and you see the drones flying. You should look like this. But then maybe another way to look at it is you can imagine we have the driver of the truck looking at the system. The drones are just flying around the truck like a horsefly, like a fly, flying, like that. So this is going to be like the trajectory of the drone in the truck driver's eye. So by translating this problem into this sort of a change of the coordinate system, then we will be able to develop this again, the PDEs in a similar fashion. And then we basically come up with some PDE based on the densities of the drones. Anyway, there's some technical details that we change the formulation a little bit, which is better because we want to ensure safety, that we want to limit the density directly. Then we were able to solve it. I'm not going to bore you with it. Again, we use neural networks to solve it. But we try the finite element, that we want to try something else. Then this is actually the solution. I just want to show you a couple of examples where again the truck is moving like that. If I were to sweep through you like this 90-degree, like this, I'm visiting you guys like that. You know what I'm saying? The truck driver's view at any moment in time, my drones are visiting customers along these two lines at the same time. Or I could do this like this. I could do that. You know what I'm saying? You understand what I'm trying to say, right? So these different solutions as choices of my service plan. And then this is the trajectories of the drones. This is how the truck driver is seeing the drones flying. This is how the roadside observer is going to see the same thing actually, but just different perspectives. And then we will be able to, I'm sure you will agree with me. We can actually play with this and then try to test the different type of speeds and different service ranges and so on and so forth. One interesting finding I remember is actually if the truck travel too fast, this may not work because the drones cannot catch up anymore. So it's actually interesting. We never expected that. We thought the faster the truck, the better. But it turned out that actually the drones cannot catch up if we were to do it in a certain way. So it's actually quite interesting. Anyway, so whatever we do here is that actually we came up with this PDE solver that we solve PDE for any combinations of parameters. Then this is like a black box we use to really design the service. The design the service is meaning for any demand we have, for a city given to us, how do we really make sure we have a plan for the truck to move around and the drones to be sent out in a way. So the idea is actually just to mention this a little bit again. Think about in an arbitrary shaped city, it doesn't then we probably should come up with a truck routing plan, go through the neighborhoods with a certain width as one part of the design parameter, hyperparameter we have, and then also the speed of the truck and all those things that we worry about. Then imagine that we have some width that we cover, and then the truck is going and the drone is sent like that. Imagine this is actually part of that. Then we now, the good thing is actually we now have a way to measure the cost of doing it. This is a solution of a PDE, of the PDE, and then that solution of the PDE can be embedded, used as a model to estimate the cost for the whole city or for the whole area. Then we will be able to, I'm not going to bore you with all the math, but we have the way to estimate it. And we were able to figure out the, essentially under different combinations of these things, speeds and delivery headway and so on, we will be able to figure out what is optimum, choices of the truck speed and width of the service, how wide we want to go, those type of things. And lastly, oh, gee, okay, I'm running out. 1 second. Is actually whatever we were talking about. One is actually assuming homogeneous demand everywhere. So PD assumes homogeneity. This is also homogeneity here everywhere. What if the city has heterogeneous demand? This is actually an issue that in reality we have to deal with. And also the streets may be varying with different densities. Certain part of the city could be very densely populated with roadways and trucks can go very easily. Other parts, maybe we have a lot of parks and so on. So in that regard, if things are heterogeneous, the idea, I'm only going to say the idea is to try to use, we partition the space into some neighborhoods. Each neighborhood is more or less homogeneous inside. And then we have the way to solve each homogeneous neighborhood. And then we find the solution for each neighborhood, we call region. Then we find a way to connect all the truck routes together, and as the truck enters this region, we have certain design regarding the speed and the width and so on and so forth. Just imagine we have all this figured out, then the last thing is to find this overall for a truck route. So this is actually very recent work that Rifeng has been doing. So just to show you that RAN2, we were working with a few of you on designing this air-based delivery. We clustered RAN2 into pieces, and then each with a more or less homogeneous demand, and more or less homogeneous street network. Then we will be able to apply whatever we had before to try to, for example, here, each of this, we will be able to figure out the cost of doing the deliveries. The last part is actually, I mentioned about this is a homogeneous area, this is a homogeneous area. We know how to do things inside, but then we just need to have trucks go around them and connect all those little regions together. We have the entire truck plan. When the truck enters the area, they do protocols as we prescribe for them in that region. Then they change the region with another protocol for the truck to follow. So that's sort of the overall idea. I will not bore you with this. We have been doing this, and hopefully some earlier results were able to measure the cost of truck, drone, combine the delivery cost and energy and so on. For RAN2 as a case study, and then even to compare it, I think recently we jointly working with our group that we were able to compare the cost and the truck requirements and so on against the human-based current way of doing delivery to RAN2. So there's some significant savings, I think. The numbers are not important. It just shows that actually there's a huge improvement we found. We try to use as realistic numbers as possible in the parameters, but it's just promise. Anyway, with this, I think I'm coming to the end. Last slide. So where are we going? I hope I've been talking about freight the entire talk, but I really sort of in my head all the time since maybe 7 years ago when I started looking at this problem is actually this cartoon from the 1950s. It's about the future of cities, and maybe we don't really drive vehicles in the next, maybe 10 years, 20 years from now, we'll be flying a lot. I don't know how soon that could happen, but that's at least some futuristic view of it. And then in that regard, then the model we have been talking about drone traffic movement in the airspace will directly apply. I hope you can see that. So we deliver people, of course, but of course in outer space, I really think maybe in the future there's an opportunity to look into the certain movements and then issues in outer space. So with this, I thank you for your attention, and then I appreciate it. Thank you. Yes, please.
Hello, Professor. Thank you for the great presentation. My first question is, how is the charging infrastructure shaping for the drones, and how will it play out in this optimization problem?
The charging, I think that's a great question. We have not thought too much about charging, to be honest. I think charging nowadays are a lot of the vehicles. I think the trucks we're talking about probably should provide the charging capacity, and then we have some. This is all futuristic. We're really envisioning what's going to happen in the future. We think it's probably best that the bigger vehicle is going to provide the charging capability for the drones. When the drone finish a delivery and come back, it can be charged on board. So yeah.
So how about if you take one more?
Okay. Okay. So two more, if that's okay. Okay, please.
Thanks for the presentation.
Yeah.
I have a question. So I understand that you are modeling this as a continuous space, right? So if you were to consider the drone dimensions and also velocity as a factor, especially on the static case, how would results might change in the condition.
We sort of, we do, our model is continuous, that's an excellent comment. But we do have this, I want to show this, we have this, we describe drone by the so-called density function. I don't know if I define it here, but this density, we have a minimum density requirement. I trying to find, there's actually the sort of a density, maximum density. That means actually the drones have to keep a certain separation from each other. See, so in a sense that actually this is actually the whole reason we actually changed the density-based formulation such that we can enforce this requirement such that actually we ensure every single drone is at least a certain distance away from another drone. Does it make sense? But when we describe the collective behavior of the drone population, we use sort of the fluid approximation. We use the flow, flux, density to describe it. But this ensures that we have at least a certain sort of a guarantee of safety.
Just very quick follow-up, like in the earlier static like a formulation where truck is going to be static and the drones, was velocity a variable? Because I saw the trajectory is the only solution that you're obtaining, right? Was velocity of the drones is also part of the equations?
I'm not sure which one are you talking about. You mean the
Previous formulation of.
this one?
Yes.
Oh, yes. No, the velocity is part of it. This is a whole. Sorry, I went too fast. I think this here. Sorry. Yeah. This C function is actually the inverse of the velocity. This is the cost or time, if you think about time as a cost per distance. So this is the cost per traveling 1 unit of distance. This cost, travel time, if you define it, is increasing with the local concentration of jobs. So it's considered. So sorry, Angeli.
Yeah, I was just curious, how do you impose a conflict? And what I mean by that is, if Amazon is serving and UPS are serving the same area with different demands and truck routing that they want to optimize, how can this model kind of incorporate it? Because the patterns at the end is serving a specific route for that entity and they're like parallel, but now you have like, how do you impose a conflict in already like a messy like problem?
Short answer, we haven't considered that. So we right now, that's an excellent question though. We are considering, so Angela's question was that actually, what if we have multiple companies running different fleets and then their drones are going to fight, right? In a way, we haven't considered that at all. So that's a wonderful question. But I think in that regard, I think it can be addressed if we really just that's actually very challenging. But think about that. We were talking about the route choice of drones in a continuous space, right? Like we're looking for the trajectory for each drone. But imagine that actually another company has a whole bunch of drones flying around. A simple approach, the first step approach, is to assume that we solve each company separately first. We solve this company, find the optimal, we can iterate. We solve this company, find all the drone movements and so on, corridor use and so on. Then we fix it and then add that back into the background. Here, this flux can include the traffic of the other company. But for now, we can keep that as a known. Then we can actually, for example, I keep A company's traffic fixed. Then we solve B company's traffic. Then we fix B company's traffic, and then solve company A's traffic. We iterate a few times, we may be able to find a sort of a way of those companies working. Does that make sense to you? Yeah. So, but that's not optimal. So that's one way to do it, I think.
One extra one.
Okay. So
Good question. Excellent presentation.
thank you.
What's the current state of practice? That's what I'm curious.
I think no, the current practice, I think, you know, I have to say I'm a little, my work is a little detached from reality, but it's all futuristic about the future. But I just want to say that actually you know, I personally think the companies have been trying to address this truck drone combination. That's a huge issue for them. The UPS has been doing it for a couple of years already. They have not been worried too much about the congestion yet. I really hope I could. Yeah.
How are the drones flying? Are they flying on their own or?
Yeah, they are actually controlled, centrally controlled, I think, right now.
Oh, cool.
Yeah.
Not auto.
There are also autonomous ones that are actually being developed. I think that's actually our mechanical engineering colleagues are working on that a lot. So self-aware and self-routed drones. My work can handle both. So we are going to allow centrally controlled and decentralized. But actually, to be honest, I'm not too sure where we are in terms of academia development because like Naira, a professor, our colleagues in mechanical are developing those type of drone local control, decentralized control protocols. we probably should ask her next time about where we are now. But I think some of these drones are.
She was here last year.
Oh, okay, yes, that's right, that's right. So they work on the hardware, I work on the soft side of managing this traffic, so. A wonderful question, thank you, yeah.
All right, well, let's thank Professor Ouyang for the